And my title for today's presentation is Waste Agricultural Plastic Upcycling, Introducing the Hydrochemolytic Technology Platform. In next 20 minutes or so, I will discuss or I'll present about what is the hydrochemolytic technology, what is it all about, what it does, and how we utilize our core hydrochemolytic technology platform for waste agricultural plastic upcycling. This slide is really about what are the plastics, how prevalent are they, and in general, to sum up, plastics are ubiquitous, they are everywhere, and they are, because of their prevalency, they are posing some sort of problems with regards to environment, with regards to energy, with regards to resources as well. So there is a need in developing the technology or technology platforms for recycling of waste plastics. And the recycling technology so far can be broadly divided into two types. One is mechanical type, which is simple, cost-effective, but has limited applications. I was just discussing with Ralph about the mechanical versus chemical recycling pathways. And another one is chemical recycling, which is a little bit more complex, but potentially unlimited and offers a lot of potentials with regards to feedstock, new feedstock, or circular economy. As a clean technology company, we have seen a tremendous interest or growth in interest in recent years in chemical recycling of waste polymers, waste plastics, and moving into the circularity, wherein the waste material becomes the feed or input material for certain other applications. As for the Aduro itself, our mission and vision is to maximize the waste plastic resource recovery by producing commodity chemicals or fuels for circularity and sustainability. That's what our mission and vision is. And when I was listening to Dr. Lisa's presentation, I was connecting it to what she presented. So she spoke about the plastic films, the mulches, and the opportunities, as well as the challenges of upcycling or recycling. And my content through my presentation, I will try to address that we are here to address some of the challenges and grab those opportunities. So let me walk you guys through what is the Aduro technology platform and how we envision that our technology can handle or can process the agricultural films or agricultural waste into value-added products. The plastic problems, we see two key features of plastic problems. One is quantity related. It's huge amount, like the amount of plastic waste generated is huge, and it's a global issue. It's pervasive, it's everywhere. On the other hand, the problems of plastic are related to its quality or its physicochemical properties. Like if the plastic did not possess the properties it possesses, then quantity alone would not be a problem. Let's think of cellulose. It's also ubiquitous, but cellulose is not as problematic as plastic. And again, like I said, the problems of plastics are not only due to the quantity, but also due to the quality. And I would say that the quality of the plastic, it exacerbates the quantity related problem. So with regards to quality, what I mean is it's diverse. It's made from polymers that have a wide range of properties and chemistries. And there is not a single most technology that can handle all different type of polymers. That's one of the problems or challenges posed by the diversity of the plastics. And they are very robust. They are durable. They are chemically as well as mechanically durable. They do not undergo degradation. They are not biodegradable. They remain in atmosphere or wherever they are dumped. They remain there for a long, long time. So that's another problem posed by the property of the plastic itself. While they are robust, on the other hand, they are not as recyclable as elements like aluminum or iron. By that, what I mean is plastics have limited recyclability. If we talk about the mechanical recycling, for sure, they have the very limited recyclability. They cannot be recycled for infinite number of times. For chemical recycling as well, they pose limited recyclability due to contaminants, due to the additives they are added during manufacturing. So with regards to the plastic upcycling, what is the moonshot? What is the bigger picture? What is the ultimate goal that encompasses the polymer upcycling, plastic upcycling with regards to chemical upcycling technology platform? Let me read it. What we see as the moonshot or the ultimate goal is, or the bigger picture is, maximizing the waste resource recovery from all plastic waste to produce higher value platform chemicals or feedstocks for circular production of plastics while satisfying the key criteria. And what are those key criteria that we have identified are maximizing the conversion, maximizing the product value, producing the value-added products out of the waste material. And the technology has to be configurable. It should offer flexibility with regards to scaling up as well as downscaling. So flexibility, scalability, overall configurability of the technology while maximizing the conversion yield and maximizing the product value. That is the key criteria for chemical recycling scope in bigger picture. Whereas the technology should be able to minimize the CapEx and OpEx, minimize the energy requirements, and most importantly, minimize the environmental footprints and emissions. There may be many more that can be added to the list, but these are the vital ones that we see as the key criteria for the chemical recycling of waste plastics or waste polymers from bigger perspective or large perspective. So I spoke about what is the moonshot, what's the ultimate goal. In order to reach there, we have to begin from somewhere. And we identify three established vehicles, three established technologies to get into the space. One is solvation, the other one is solvolysis, and the third one is thermolysis. Solvation is a technology which uses the solvents to selectively solubilize certain type of plastics or polymers, while certain other types of polymers or plastics are not soluble. So this leads to the separation of the components or different type of plastics from the mixer. A quite good example of this technology is, which is what is called solvent targeted recovery and precipitation, abbreviated as STRAP methodology, that was published by the research team of Walker, and that was published in 2020. And that talks about the use of solvents depending on their solubilizing ability to separate the plastics from the mixer. In solvolysis, as the term suggests, it is the addition of solvents to the polymer bonds to break the polymers into the smaller units, which are called monomers. So solvolysis is a technique wherein the large molecular weight polymers are depolymerized by the use of solvents. And depending on what solvent is used, they are classified as hydrolysis, methanolysis, glycolysis, etc. And this technique is used mainly for, or applicable mainly for the functional polymers like polyesters, polyamide, polyurethanes, etc. Here again, I would like to bring my conversation with Ralph just maybe a 5 minutes ago. He was saying that PET is the one that has a long history of being a recyclable material. And that is because, to my understanding, that is relatively easy to recycle because that undergoes the well-known solvolysis chemistry. And by solvolysis, that can be deconstructed or depolymerized to the starting monomer units. The third one, another one is thermolysis, which utilizes the high temperature to break the bonds in the polymer molecules or plastics. So it works by rupturing or breaking the chemical bonds and rearranging the molecules by decomposing the larger molecules into smaller ones. An example is the gasification. Since relatively high temperature or high amount of energy is used, it's a very random process and it gives rise to the mixture of products, very complicated mixture of products. Here, I would like to connect quickly to the problems or the challenges that was mentioned by Dr. Lisa with regards to recycling. Yes, all these techniques, solvation, solvolysis, thermolysis, they have the limitation that they cannot handle the plastics or waste plastics that are contaminated with soil or dirt or sand or etc. But we have another new vehicle, which is hydrochemolytic technology. This is Aduro proprietary patented technology, which is a very simple water-based technology, and it is capable of upcycling waste agricultural plastics to high-value hydrocarbons, feedstocks for circular economy, and for generation of fuels as well. It is a unique conversion process wherein we use transition metal salts as metal catalysts that are readily available, low cost, and readily recyclable. So those are the key of our process. Along with the catalyst, we use some compounds, chemical compounds like glycerol, cellulose, or any components that can be recovered from waste plastics, like ethylene glycol that can be recovered from solvolysis of PET. So those type of compounds are added in our technology in a small proportion, and they act as a source of hydrogen equivalent. What they do is they eliminate the need of molecular hydrogen as that would be needed in traditional thermolytic or pyrolytic approaches. So because of the combination of the very simple chemistry using water, readily available metal catalyst, and hydrogen equivalent sources, our technology is highly efficient. It has the ability to transform the plastics or polymers in high yields at relatively low temperatures to value-added products. Little bit of a chemistry about how polyethylene is made and what is the degradation chemistry or chemical deconstruction pathway or products generated out of that. Polyethylene manufacturing, it begins from cracking of naphtha or natural gas liquids in ethylene cracker or naphtha cracker producing ethylene. Ethylene is a two-carbon molecule consisting of a double bond between two carbon atoms, and that undergoes polymerization using very specific chemicals, reagents under specific conditions to produce polyethylene. That's an example of a polymer that I have taken. And in that polyethylene, it consists of carbon-carbon bonds, huge number of carbon-carbon bonds bonded with each other and a cross-linked structure as well. And the part of the structure that I have shown there consists of two carbon atoms bonded with each other and also bonded with other carbon atoms. And this is an alternative representation of polyethylene. And that number of X or number of yen in that polyethylene structure, it can range from several hundred to several thousand units. So you can imagine it is a very, very huge macromolecule. What our technology actually does is, in our technology, we produce the intermediates, we produce the reagents, or our reagents, they act as if like they are the chemical seizures, and they break the carbon-carbon bond of that polymer chain. This carbon-carbon bond breaking is a little bit random, But we control the technology, we control the process parameter so that we have a control over the process parameters, and we have some sort of control over the composition of the product as well. And after hydrochemolytic deconstruction of this polymer, the monomers or the compounds we generate, not the monomers, the compounds we generate are low molecular weight alkanes. In the slide I have shown there, carbon number 10, 12, and carbon number 15 hydrocarbons. That's what we generate from the polyethylene. A little bit more about the energy related to this construction and deconstruction. The picture shown here is, which is what is called energy profile diagram. In the energy profile diagram there, on the x-axis is the progress of reaction, and on y-axis is the energy. You can see that the ethylene molecules are sitting at the energy level with certain amount of energy. They already possess certain energy, but they do not undergo polymerization on their own. It needs a catalyst, and that catalyst provides the sufficient energy so that those ethylene molecules, they go through that hill and then turn into polyethylene. And once it is converted to polyethylene, this molecule lies in so low energy level that it is very unreactive and very stable. And what makes polyethylene so stable is the low energy that it has. So deconstructing polyethylene and going back to ethylene is going back through this hill energy barrier, and that needs huge amount of energy. So what our technology does, hydrochemolytic upcycling does, is we use the catalyst, we use a little bit of heat energy lower than 370 degrees centigrade. And by combining that polyethylene is deconstructed to paraffins of varying carbon chain length, and it is below carbon number 50. And like I said, we can control that distribution by controlling our process parameters. If I were to compare our technology with the traditional thermolytic technology, this is what it looks like. In pyrolysis technology, it requires a substantial amount of energy in order to break or decompose the polyethylene into the complex product mixer. And that is why traditional pyrolysis or thermolytic technologies are very high energy intensive, and they always produce a complicated mixer of products. So from this, I believe you guys can see the benefit or the uniqueness of our technology, that it can do the same job in a better way, utilizing the catalyst and a little bit of energy as compared to, much less energy as compared to the pyrolytic technology. That's where we stand differently from traditional pyrolysis and solvolysis and solvation technologies as well. We have done many experiments in lab scale for proof of concept, wherein we combine the plastic, water, catalyst, and our hydrogen source in a hydrochemolytic reactor that goes post-processing. We generate a little bit of gas, major proportion of liquid, and some solids, and we analyze the gas, liquids, as well as solids. The picture I have shown here, it is the picture of one of the products that we have obtained from one of our runs, and that has the pour point or melting point of 60 degrees centigrade. And this product has very high purity. Let me explain what is that high purity is. So here I have summarized the process conditions and the mass balance of our technology. Polyethylene feedstock, after hydrochemolytic technology, it produces, like I said, liquid as the major proportion, some gases, some solids. Liquid is 85 to 90%. We generate 3 to 8% gas, and some solids, which is unconverted plastic material, as well as some ash or impurities present in the plastic starting material itself. With regards to the process conditions, like I said, water is one of the main ingredient. We use water and plastic or polyethylene ratio in somewhere in 2 to 1 to 4 to 1. Operating pressure is 1,000 to 3,000 psi, and temperature range of 300 to 400. This is the highest range, but all our operations occur at temperature lower than 375 degrees centigrade. Here I present a chromatogram of the liquid product.
Birendra, I'm sorry to interrupt you, but you need a little bit speed up. We're running.
Okay, I'm almost done.
Okay, good. Thank you.
Yeah, this is the liquid product. This is the composition of the liquid product that we get. And this tells that our liquid product composition ranges from carbon number 10 to carbon number 35. And we can change this distribution towards the left-hand side or the right-hand side by tuning our process parameters. So I'm going to skip this. So here I present the cradle-to-cradle pathway of polyethylene life cycle, wherein ethylene undergoes polymerization to produce polyethylene, to produce molded polyethylene products. And after post-consumer recovery, we utilize our hydrochemolytic technology in ethylene to produce the feedstocks for ethylene cracker. And that goes in ethylene cracker to produce ethylene and polyethylene. So that completes a polyethylene life cycle. And utilizing Aduro hydrochemolytic technology, we play a pivotal role in circular economy of polyethylene. Due to the simplicity, reliability, and clean nature of our technology, Switch Energy became interested in partnering up with us, and we are partnering with Switch Energy for the installation of the pilot plant in Ontario for processing the agricultural films. And this is where we are currently standing. And if any of your mission and vision echoes with our mission and vision, here I am offering that we are open to discussion and we are open to do the customer testing. If you have any material that you would like us to test, how our technology treats that, you are more than welcome, and we are ready for customer testing as well. With this, I would like to acknowledge my team and thank you so much for your attention and listening to me.